So in machine learning, there's three types of learning algorithms. They're supervised, unsupervised, and reinforcement learning. Supervised is when we have an input set of features or variables from which we're trying to predict an output variable called the label. And supervised, essentially, it's called supervised because we have got training examples that the machine, that the algorithm, like data that we've collected from the mappings of input variables to output variables, which the machine can try and use to learn that mapping. Unsupervised is when we don't have that data of mapping from input to output, and it has an essentially different goal. It's trying to find either different representations of the data or try to find classes or clusters inside the data and other stuff like that. And reinforcement learning is a quite different paradigm to the previous two. It's a lot more to relate to how humans work and animals. It's essentially you put an algorithm in an environment and it tries to maximize rewards which you give it. So supervised, there's two different types of supervised algorithms. One of them is called regression. And regression is when we have an input variable from which we're trying to predict a continuous output variable. So we could have something like this, like X being the number of rooms in a house and Y being the price of it. And let's say we've gone out there and we've actually measured the number of rooms in a house and we've actually collected the data about its price, and we can plot it like that on our graph. So the task of regression would be to find a curve or a line that best fits this data. In this case, it would just be a straight line going like that. And what this allows us to do is, based on a given input, such as 5 rooms, I can then predict a price for it, which can be very useful. And then there's classification. So that's essentially if we had something like number of rooms in a house, and then Y represents the probability that that a family lives there. So 0 would be a family doesn't live there, and 1 means a family definitely lives there. And we could have some data points again, such as this. I'll use X to represent that a family doesn't live there, and then O to represent that a family does live there. And what our classification algorithm would be trying to do is essentially find a line, something like that, that best allows us to, based on the input variable, predict whether a family does live there or not. An example of a 2-variable classification problem would be something like this. Or we have 2 input variables, x1 and x2, and then we plot them again like something like that. And our algorithm would essentially be trying to find a line such as this one. If you can say that if the data point is above this line, then a family does live there, and if it's below this line, a family doesn't live there. Okay, so on to supervised. I'm going to be showing you one quick example, which is called clustering, and that's essentially if you have data points. Let's say this is a 2-variable clustering problem. So you have different data points such as this, and these don't have classes. All you know is that these 2 bits of information about them, and you ask the algorithm to essentially create the classes for them in terms of the similarities between the variables. So it could probably try and find a line like this and say that's the best way to cluster your data, because these points are very close to each other, and these points are, and these 2 groups are very far from each other. So reinforcement learning is essentially when you have an agent and an environment, which I'll just write env, and then this agent is free to take actions inside the environment, and it receives back an observation, which we'll call O, and a reward, which we'll call R. So an example of what this could be: the environment could be a chessboard, and the agent is the computer player that's taking the moves on the board. So it receives an observation from the environment, which is essentially the state of the board, where all its all its pieces are, etc. And then based on that, it takes an action, moving its piece to a certain place, and then it receives again a new observation, how the state of the board has changed, and a reward, which is essentially tells it whether that move was good or not. And all the algorithm tries to do is to take actions given observations to always try and maximize reward. What I'm going to be covering now is linear regression. So if you remember, in the supervised regression problems, we're trying to find or predict the value of an output based on an input. In a linear regression, we're assuming that the output is a weighted sum of the input features. So in a linear regression problem, we have something like x is equal to, we have some data set. This is our input variables. So we have something like x1 of 1, x2 of 2, all the way down to x1 of n. And n is the number of features that we have. And we then have x of 2, and each one of those has the same, x of 3, all the way up to x of m. M being the number of examples that we have. M is the number of data points, and n is the number of features. So for each data point, we have 1, 2, 3, n features. So that's an n by m matrix. And then we also have a set of labels. So for each, so we can go along with the example. Let's say the number of rooms in a house and the number of windows. So in that case, n would equal to 2. So we'd only have 2 input features. So based on the number of rooms and the number of windows in a house, we can try and predict the price. So we can say y, we have this is our data set again. So y of 1, y2, y3, ... all the way y m. So each one of these represents for that given input, what was the price of the house? For those given features, what was the price of the house? And this would be a 1 by m matrix. And then what we're going to do, we're going to initialize some weights, because what we're assuming is that h, our hypothesis, which is what we're going to predict the price of a house to be based on its inputs, we're going to say h equals w times x. And what w is, that's also a vector, and that's essentially w1, w2, w3, ... all the way up to wn. So that's a 1 by n vector or matrix. So when we multiply that by that, what we get is our hypothesis. So that's our predicted value for the price of the house. So to show you in a graph what that looks like, if we assume that we only have one input, we might have some data points such as this, and so h could be initially something like this. That h is essentially the line that we're predicting to use to model the data. So h initially starts out something like this, and what we're trying to do is find something we call w star, and that's the optimal hypothesis. So w star might be something like this. H star might be something like that, and each h star has a w star, which is the optimal weights which draw this line essentially. So what we're trying to do is we're trying to constantly change h. We're trying to bring it closer each time until we get h star, which best models the data. So how do we do that? Well, we define something called j, and j is essentially a measure of how wrong our prediction is. So if you look here, this line is a bad model for that data, because if we take the sum of the squared distances for each and we square it, because we care about the magnitude of it, not its actual value, and because let's say if we had some points here, we don't want our errors to cancel out, we want them to sum up So we take the magnitude. So if we take the magnitude of each point from this line, we would have a much higher value for that sum than if we were to do it for H star, for example. And that's because H star predicts, models those data points much better. So we can say J, which is our error, J is equal to 1 over 2m, that's essentially to average it, over the sum of I equals 1 to m of h minus y squared. So what we're essentially doing is for every example, let me just put I there. So what we're doing is for each example that we have, we're predicting what the value should be using our model. So we're getting hi, and then we're taking that away from the true value of it, and then we're squaring that to get the distance of it, and then we're summing it over each data point, and then of course we're averaging it. So now we can see that our goal is to minimize this error. We want to minimize the distance here and perfectly predict that. So what we can do is we can calculate. So let's say we had the value of our weights here, W. Let's say in this case it's a single variable, so there's only one W. And then we have J. And then let's say that the sum it follows that function essentially, J and W. So what we can do is initially randomly initialize our W, our weights, and we can end up on a spot like that. And then on there we take the gradient. So essentially the gradient tells us the direction of highest increase of J. And what we can do is we can take a step in the opposite direction. So we can change our W by this much, by that much there, for example, and then we will land on this part of the curve, which means that we have a lower J. And then we constantly keep doing this until we end up at the optimum value at which we've minimized J, which is our error. So how do we do that? So we define something called dj by dw, and this is the partial derivative of J with respect to each weight. And what partial derivative means is that let's say because we have many weights, then we want to find how we should change every single weight to reduce our J. So we call WK, for example, for any weight. The partial derivative of it is equal to 1 over m times the sum hi minus yi squared times xk. Sorry, not squared. So what we've done essentially is we've used the chain rule, because h equals wx. So if we were to plug that into there and then take the derivative of it using the chain rule, we would end up with this. And what this allows us to do, if we know which direction is a direction of steepest gradient, what we can do is we can say w of k is equal to w of k minus alpha times dj by d omega k. Sorry, it'd be dwk. So what essentially we're doing here, that's this step when we're updating our wave values, and we're doing that with multiplying it by an efficient coefficient called alpha, which is called the learning rate. So what the learning rate essentially allows us to do is to control the size of the steps that we're taking in the direction to minimize J. And so why would we want to do that? Because let's say that at this point our gradient is extremely high. So what that means is that we'll do WK minus that gradient, and if WK is extremely high, that means we might end up taking a step like this. For example, we could step all the way down here, and then we could possibly converge to this minima, or we could take a high gradient again and we could jump to over there and keep on jumping around, and that way we're converging rather than we're diverging rather than converging, which is what we want. And let's say, you know, we get down here and it's too low. The value of the gradient is too low. What that would mean is that we take tiny little steps until we get to the gradient, the optima, which is not what we want. So if the value of alpha, the learning rate, is chosen correctly, what that can allow you to do is choose a number of steps such as this, and you could get to the minima in the smallest number of steps. Because every time you're doing this calculation here, you're using computational resources. So the more you do it, not only the longer is it going to take, but it's also going to waste more computational resources. And to give you a bit of an intuition of what these weight values mean. So let's say that our input variables are the age of the people that were living in a house, the number of windows in a house, and the number of doors in a house. So we would expect for the W, like the coefficient of the number of rooms in a house, to be very high, because the bigger the number of rooms, the bigger our output. Why? The more the price of the house. And we'd expect the number of windows to also be positive and high. Or we'd expect, for example, the number of the age of the people living in the house, the weight for that a feature to be 0, because the output variable doesn't depend on it at all. But if we also had another one, such as the age of the house, then we would expect that to be very negative, extremely negative, because that's essentially the older the price of the older the house, the lower the price of the lower the price of it, because that has like a negative impact on the price of the house. So today we're going to be implementing those algorithms and using a Python library called PyTorch. And PyTorch is essentially a general computation library, meaning it allows you to do any form of calculations and operations on huge, n-dimensional tensors very easily. And a tensor is essentially like a matrix, but it has more dimensions. So a vector is one-dimensional, matrix two-dimensional, and a tensor would be a three-dimensional tensor would be 3 dimensions, or 4 dimensions, etc., etc. So so that's why one of the reasons why we use it. Another reason that we use it is because it has something. So while you're doing these operations on tensors, what it does is it builds something called a computational graph behind the scenes, and I'm going to be explaining to you, what computational graphs are and why they're useful. So we could have some equation, let's say like before, where we had the equation h equals wx, and then we had j equals h minus y squared for each example. This way we just calculate it for a single example, but you could sum over all the examples and then divide by m to take the average. So how can we model these mathematical equations in a computational graph? We start with x and w. So what I've done here is I've created 3 nodes in my graph. These nodes are essentially inputs, so I've made them square. But these are essentially just like that, except for we put values into these rather than them being calculated from other variables. So what happens here is these 2 nodes are fed into this node, which is essentially like a multiplication node. And what this outputs is x times w, which is h. So we can just call that node h. So now we want to figure out j. So what we do is we also feed in y, and then that feeds into another node, which does essentially a takeaway node, which outputs h minus y, and we can call that, let's say we call that d, and d is essentially just the difference between those two. So now that goes into something like a square node, which outputs us j, because j is equal to h minus y. Okay, so why would we want to represent our computation like this? Because now what we can do is, let's say we're trying to find the optimal values for w, as in the case of linear regression. What we can do is easily find the derivative of this node with respect to that node. So what we can say is j is equal to d squared. So the derivative of j with respect to d is equal to 2d. And now we can say d is equal to h minus y. So the derivative of d with respect to h, because we're trying to go this way and find it for w, is equal to 1. Now h is equal to x times w. X times w. So now the derivative of h with respect to w is equal to x. So now if we want to find the derivative of j with respect to w, we just multiply those along, just like the chain rule. So we say dj by dw is equal to dj by dd multiplied by dd by dh multiplied by dh by dw. And that's essentially equal to 2d times 1 times x times 1 times x. And d, as we know, is equal to h minus y, which is equal to d is equal to h minus y, which is equal to xw minus y. So now we can just pop that in there. We can say dj by dw is equal to 2dx. So just using this computational graph, the Python library PyTorch can easily work out the derivatives using this process, essentially called automatic differentiation, and allow us to optimize our equation for any single variable just by using those partial derivatives. So now Harry is going to show us how to implement this using PyTorch. So now for the implementation of it. So the first thing we're going to do is import Torch, and just to show you, how similar Torch is to NumPy, PyTorch is to NumPy, we can do x is equal to torch.tensor, and then we pass in an argument such as a list or a NumPy tensor, essentially a NumPy matrix, essentially any kind of list that it can turn into a tensor. So I can say 1, 2, 3. Here I'm passing in a standard Python list, print x. So we get a value of 1, 2, 3. So if we do, and it shows there that's a torch.float tensor of size 3, and a float tensor means that it holds floating point values. So what I can do as well is I can do y is equal to torch.tensor of, let's say, 1, 2, 3, but this time it's a column vector rather than a row matrix. Here it shows them as the same. So what I can do then is I can do print torch dot which means matrix multiplication of, and I can say x with y. So that's giving me an error there, because that's saying the first tensor that I've defined here is just of size 3. It's not a matrix, so I can't do matrix multiplication on it. I can dot product it, but if I want to do matrix multiplication, I have to specify that this is a 3 by 1 and not just a 3. So if I do that, should get the answer, which is 14. Okay, cool. So we'll begin with defining some hyperparameters. You'll see why these are defined pretty soon. So let's say n, which is the number of features that we have, is equal to 2, m is equal to 500. We'll also define right now a learning rate, which is equal to 0.5, and a number of epochs, which is equal to 150. And you'll see why we've done all these hyperparameters in a second. Say dataset creation, hyperparameters, and training hyperparameters. So what we're going to do, we're going to create a fake dataset. So what we'll write here is import as well. From torch.autograd import variable, and this is just the type. Variable is a class which we're going to make objects from, which essentially defines a node on the computational graph, as you saw earlier. So what we can do is we can say, okay, data set creation. So we're going to create a fake data set here just so we can test our algorithm. So we say x is equal to variable, and to initialize a variable, a node on our graph, we have to give it some initial values. So we'll say it's equal to our torch.run n of n by m. And what this is essentially doing, it's initializing an m by m matrix of random values between 0 and 1. And we can say that those are our inputs. And those can be, for example, the square mileage of the garden of a house, and the square mileage of the base of the house where over which all the rooms are. And then y, we can say, is equal to another variable. It's a node on our computational graph. 0.5 times, and if we want to get the values, the tensor stored inside a variable object, what we have to do is x.data to get the tensor that's stored inside, and then from that tensor we want the 0th row and all the columns, and then add let's say take away 4.2 multiplied by x.data again, this time of the first row, all columns, and then plus 2, just to give it a bias. So what this is saying is that our price, we're creating the data set here, so we're saying for these houses the prices are equal to 0.5 times the square mileage of the garden, 4.2 times the square mileage of the rest of the house, plus 2, just because just to give it a bias essentially, because even if a house, well, in this case what we're saying is that house with no square mileage is actually worth something. So and this value could be in thousands, or anything like that. So it doesn't really matter. It's just how we interpret it. So now let's say W, that's our weights, and W, as we saw, is so we'll define it as a variable. It's and we'll give it an initial value of random of 1. It's a 1 by n matrix, and what torch.randn does is it gives it values with a variance of 1 with a mean of 0, so they're centered around 0. And then what we have to do is say requires grad equals true, because what torch essentially, it has this function which allows us to compute our gradients with respect to each variable. So every variable that we're trying to optimize, we have to let torch know that that particular node on the graph is a node that we're trying to find the derivatives with respect to. And we are trying to find the derivatives with respect to the weights, because that's what we're trying to optimize and change. And what I'm also going to define here is a bias, which I didn't show in the example, but
But a bias essentially allows us to map functions, linear functions, which don't this time go through the origin, because if you have no bias, that means you're always, y equals mx plus b. If b is always 0, then you're always passing through the origin. Okay, so now that we've created our data set, what we can do is run through the iterations. Like we said, we're going to be constantly updating our weights to go in the direction which minimizes our losses. So we'll say for epoch in range, no epochs, and here is a hyperparameter which we defined before, and an epoch is essentially one run through of the whole data, and basically taking it's calculating the derivatives with respect to all of our data points, and then taking the necessary steps. So in this case, we're not doing something called batching. Batching is when you look at when you try to optimize your values by looking at, let's say, 32 examples at a time. But the way we're doing it, we're looking at our whole data set at once, and we're taking the little step on the graph to change our weights. So now let's say our hypothesis h is equal to torch.mm matrix multiplication of w with x plus b, and then our cost is equal to torch.sum, because we want to sum over all of them, of h minus y to the power of 2, and then divided by 2 times m. And if you refer back to the equations, that's exactly what we defined it as. So now we run a function called cost. Well, actually, this torch has a function which is dot backward, and what that does is every variable in your computational graph will have this function. So I can call it on h dot backward or cost dot backward, and what that does is do the going through. It does essentially like the back propagation, essentially, of like taking the partial derivative of each node with respect to the ones before it, and then it basically outputs us a gradient for each one of the variables which we've defined to require a gradient earlier. So here w and b, it's going to find the gradients for with respect to cost. If we did it with h, it would do it with respect to h. And when it's got that, it stores it in a variable called grad. So if we do w, so our weight dot grad, that is essentially a variable that contains a tensor which contains the variable with respect to the derivative with respect to each weight that we have. So all we have to do is, like we said, w.data, because we want to update the tensor stored inside the variable, because each variable is just a node on the graph, and if we want to get the data inside, we have to refer to the data inside it by saying w.data. So I can say I think I used So I can say w.data is equal to minus equals, which essentially just means is equal to w.data minus LR times, so that's our learning rate, which we defined here. And so we say, so w.data is equal to w.data take away learning rate multiplied by w.grad.data. And then we do the same thing for our biases. And then we can do print epoch cost. So we want to get the cost dot data 0. We want the 0th index of the tensor stored inside cost, and cost is actually a 1-by-1 tensor. So yeah, it's essentially a scalar. We just need to make sure we're getting that first value from it. So now, if we run this, variable, yeah. Oh, I've done that twice here. Variable. No epochs. No epoch, I said here instead of no epochs. So there we go. Then, as you can see, our cost starts at 1.1 and it keeps going down. But here we can see that it's gone up again. That's suggesting that if you remember what I said about setting the correct learning rate, what that could suggest is that we're using too high a learning rate, so it's converging a bit and then diverging again, and then converging a bit and then diverging. So from the stream of numbers, that kind of thing is extremely hard to tell. So what we can do is we can plot our loss with respect to each epoch. So what I'll do is I'll import matplotlib.pyplot, that's PLT, and then I'll make I'll just define here. I'm just going to define, I'll say for plotting cost, and I'll say j's for all of the j's is equal to an empty array. And then what I'm going to do is I'm going to do plt.ion, and that just means that just sets interactive mode on for matplotlib.pyplot. And now we say, okay, so we say fig is equal to plt.figure, ax is equal to fig.add subplot 1 1 1. Yeah, so this is a 1 height, 1 row, and then this is the first axis on our figure. So x.set x label. On our lex label, it's going to go iteration or epoch, I'll call it. And on our y label, we're going to have loss. Now we're going to set well, we don't have to do this, so I'll show you without it first. Then I'll show you why that makes it a bit easier to view. So anyway, plt.show. So now each time we do that, what we need to be doing is after we've calculated our cost, we want to say, oh, okay, yeah, I've just realised another problem. Well, we'll see it in a second, but so costs, sorry, j's dot append j. I've called. Oh, okay. So here I've called this cost. This variable essentially equal to j. So I'll say j's dot append cost dot data 0. Okay, so it's not showing. Okay, yeah. Because what we're not doing is we're not plotting it. So what we want to say is ax dot plot cost. I'll just rename j's to costs. I'll make things a bit easier. Costs. Again, okay. So that's what our costs are doing. So okay. So the reason it's not updating is because I have to do fig dot canvas dot draw each time I've updated my plot. So as you can see, with every epoch it's updating, and this is going wild. So what we can do is we can try a lower learning rate, see if that helps. It seems to be getting better for a while, and then it gets worse. It gets better and then worse. So what could be going on here? You know, we can try an even lower learning rate, but again, it will show the same behavior. I know it will show the same behavior because I know what the error is here. But if you were to keep this going over a longer period of time, you would see that that will go up again. So what's going on here? There we go. It's going up. So what's going on here is that each time we run cost.backward, what that's doing is it's adding the current gradient to this variable w.grad.data rather than setting that variable to the current calculated gradient. So unless we set the w.grad.data to 0 each time after we've calculated it, we're going to essentially be storing in this variable the accumulated past gradients, and we don't want that. So what we'll do after each time we've done that, we'll say w.grad.data.0, and that just sets it to 0, and we'll do the same for b. And let's put our learning rate back up a bit. So okay, let's get him better. Let's try an even bigger learning rate. No, that's just shot straight up. That's shooting straight up, which means it's diverging, so I don't want that. But now, if we look, that's an optimal gradient because it's gone extremely low, and it's flattening out, meaning it's essentially just sticking around a certain optimum. Okay, cool. Yeah. So obviously, as you can see, having this this graph helps you easily diagnose problems that you might have, such as too high a learning rate or too low a learning rate. And what I'm going to do here is actually just do ax.set ax.set xlin, and what that's going to do, if I show you xlin 0 to no epochs, and that just means fix our x-axis so it's always showing values between 0 and our number of epochs. And yeah, as you can see, this is still printing out those values. So yeah, this works now. So what we can do with this, we can do print at the end optimized weights w.data. We can do optimized bias. We can do b.data. And then what we can also do is we could say like test is equal to torch.tensor, and this will be let's say this is just some value that I wanted to predict, so I can put in something like 5, 10. So this is a 2 by 1. This is a 2 by 1 because it's a single data point, 1 being the number of data points. So now out is equal to torch.mm of w.data with test, and add it to b.data. Now we can print in for 510 is equal to, and then we print out. So as you can see, that's still going, and we don't have to run it for this many epochs. This is another thing that graph helps us do. We can see that after 40 epochs, our loss isn't going down that significantly. So we can just stop running it then and say that we've optimized it. Okay, yeah, and if we look here, the biases, so the true values of these, the true values of these two variables are 0.5 and negative 4.2, and the true value of this is 2 because we've defined that up here. So you can see it does actually optimize and get extremely close to the true relationship, the true equation which maps output from input. and yeah, and that just gives us 5 times 0.5 take away 4.2 times 10 plus 2, and that should be it. That should, well, sorry, 0.5.0004 and that. So this is essentially what it's guessing it to be. It's probably minus 37.5, the true value of this. Okay, cool. So now, how can we, better visualize our data? Because I talked about the hypothesis, right? So how can we visualize the hypothesis that we have here? Well, given that we have two input features, our hypothesis won't be a line; it will be a surface. So I'll just show you what that looks like. So first we say so for plotting first we'll plot our data points, and then we can plot our hypothesis to see how closely it approximates those data points. So we can say ax1 is equal to fig dot add subplot, and now we'll have to change this here because this will have we want this to be 1 height and 2 across, so we'll say we'll just change that and we'll put this as 1 2 2, meaning it's 1 height, 2 across, but this is the second figure, sorry, the second axis. So now we can do ax1 dot scatter. So we want to plot those data points as a scatter plot. So we say all of the first input features dot data, and then x of 1 dot data, and then we want to plot that against y dot data on our z-axis. So I'll just change the labels for that. Label x1. So I mean, these can be arbitrary x1 and x2, but to give it some context, this can be like area of garden in square miles, or square meters, area of house. Then we can say price, and so what this will do, and we'll just actually have to put out plt.show down here so it shows this figure as well. So what we want to do as well is we want to plot our surface, and to plot our surface we need to have essentially we need to calculate the value for each point, for each values of x1 and x2, area of garden and house. We want to predict the price and then plot that. So we'll do for plotting hypothesis surface. And actually, just real quick, what we need to do is import another library so that we can plot 3D surfaces. So we'll do from mpl toolkits. So it's 3D, and we're also going to import NumPy, as you'll see why in a second. So now we, to plot our hypothesis surface, what we need to do is, we need to give into our model like every possible value of x1 and x2. So what we're going to give that as is called a mesh grid. So I'll just show you how that's done. So x1 is equal to np.arrange 2, x2 is equal to np.arrange 2. So this is giving me values between 0 and 2, so it's going to give me 0 and 1. And then if I do this, np dot mesh grid x1, x2. So what this np.mesh grid will return is two matrices, and if I combine the indices of each matrix, it will give me all the input space for this 2D surface. Well, in this case, between 0 and 2. So, so yeah, now that we've got that, what we can do is just really quickly here, we're going to change this to projection equals 3D. We need to set that so matplotlib knows that that's a 3D plot. And okay, yeah, so we've got that, cost.append, x.plot. Okay, here we're going to do calculate hypothesis surface. So we're going to say y is equal to x1 multiplied by w.data of 0. So this is taking my x1 values and multiplying them by the weights for my x1 values, and then I do the same thing for so I do x2 multiply w.data 0, 1, and then I add my bias, so w.data 0. So this is taking this is essentially calculating the height of the surface at each point on the x1 and x2 plane. So now I can say my surface is equal to, like, S is equal to ax dot plot, sorry, ax1 dot, because we want to plot it on our second axis, plot surface, and we want to plot x1 against x2 against our calculated y values, and we can set the color equal to, and this just takes RGBA, or so what that means is we want 0 red, let's say 1 blue one green and 1 for blue, and I'm going to put an opacity of 0.5, and what that will allow us to do is to, even though we've got the surface, it'll make it slightly transparent so we can see our data points through it. And now what I'll do is yeah, and after each time essentially that we've done this, what we want to do is do s.remove, because if we don't do that, it's going to plot us a new surface each time. It's going to overlay them, which you know doesn't make it easily visible. So each time we're going to remove our current surface and replot this updated one. So if I run that, okay, I'll need to make that a bit wider. So I'm just gonna, you know, and this is the kind of thing I always do, just go on Google and look up the parameters of this function to see how we can change it to make it wider. So I can do Google, I can do matplotlib, and we want to change the parameters of, for example, add subplot, or actually it's probably when we're defining a figure, because we want to change the size of the figure as a whole. So if we just go here, we can see here that it takes in as parameters these things, and it takes in something called fig size. So what we got to do, we got to change, we got to feed in a fig size to make sure our figure is big enough, and it says it's width followed by height. So what we can do is config size is equal to, we want our width to be double our height, so we say 10 by 5, for example. And here, okay, yeah, so if I put my learning rate down now so it learns a bit slower, so you can see how slowly over time that surface, our hypothesis surface, is changing and it's getting closer and closer to our data points. It might actually be a bit hard to see from only one angle, so what I'm going to do is I'm going to essentially make our view rotate around slowly as we watch it. So what I'll do is I'll say in here, I'll say ax1.view init, and what this is essentially does is the parameters of our in view in that particular axis, which is the first axis rather than the 0th one. So we say ax1.view init, and then we define an angle. But this time, what I'm going to do is I'm going to say the angle is equal to epoch. So each time it increments the angle by 1, therefore rotating it round, and we can get a good view of all round of how that surface is updating. I might put the learning rate a bit higher just to make it easier to see, because it's moving very slowly right now. So there you can see it's changing a bit faster, and it's going to more and more closely match our data points. And if I just leave that to run, oh, it does remove it to the end, yeah. I forgot to put that at the end, but we can change that. But anyway, yeah, so you did see that that surface moves closer and closer, and therefore our algorithm is working as expected. And yeah, and that's it. That's how you implement linear regression using PyTorch. There are other ways to do it. There's a much simpler way, and that's covered in the bonus video, but we really wanted to show you how you guys, because this kind of thing is what allows you to implement custom algorithms in PyTorch. Because there are a lot of built-in models, but I want to show you guys how you can translate the equation of any system into a PyTorch implementation that you can run.